Next up, we have a type of series that's called a telescoping series or sometimes a telescopic series. And this is another type of series where we will be able to compute the nth partial sum and therefore we'll be able to compute its limit. The difference though is unlike the geometric series that has a very specific form that we can write down, telescoping series, they don't really have such a specific general form that we can write down. But there is a property that their nth partial sum will always have. So that's kind of the defining characteristic of the series. Not necessarily what it looks like, but what's going to happen when you compute the nth partial sum, right? So let's just state what that property is. So a telescoping or telescopic series is one in which the nth partial sum always simplifies. So it always simplifies to the same number of finite terms. To the same number of finite terms. Again, that doesn't really tell us much, right? And there's not much more kind of build up or theory or definitions. We really just have to see an example. So let me give you an example of what a telescoping series is and then kind of show you what the process is like. And then through the process, it will become clearer what this property really means. So let's start with an example. Suppose we have the series, so let's consider this. Oh, wait. Let's write that. So consider the series k going from 1 to n, and suppose we have, it's the quantity 1 over k plus 1 minus 1 over k plus 2. Right? Oh, forget my infinity there. Right. So that's our series. Right. Again, and all we have here is we have the difference of two fractions. Right. There's nothing that really stands out about them. Maybe in the denominator, what's interesting is the fact that these expressions represent consecutive integers. So let's take a look at what this series would look like if we wrote out the first few terms, right? And again, I'm not going to do too much in terms of simplifying. I'm just going to write out what those terms are. So take a look at the first term is when k is equal to 1. Well, when k is equal to 1, this denominator is 2, and then this denominator is 3. So we have that. And then plus, when k is equal to 2, this denominator becomes 3, and this denominator becomes 4. So we should see the pattern now. We have 1/2 minus a third plus 1/3 minus a fourth, then be 1/4 minus 1/5, and so on. Right? So that's the pattern. And the question is, what happens if we, add these terms up um, infinitely often? Right? What's going to happen to them? Well, again, our procedure is to find a formula, right, for S sub n. Right? So S sub n, the sum of the first n terms. In this case, because my index starts at 1, then I'll have to go from k equals 1 to k equals n in order to get those first n terms. So here's our nth partial sum. All right, so the sum end there is the same, k plus 1 minus 1 over k plus 2. So let's write these down, kind of like what I was doing here, right? But what I'm going to do, let's list them vertically. So I'm going to list the terms in parentheses. I'm going to list them vertically. So we know that the first term is, well, it's the same expression I have right there. It's 1/2 minus 1/3. And then plus, when k is, so in fact, let me write down kind of above this. So this is the term that corresponds to k equals 1. The next term, the 1/3 minus 1/4, that's the term that corresponds to k equals 2. Right? And then plus, and then the 1/4 minus 1/5. This is the term that corresponds to k equals 3. So I need to continue this process, but not indefinitely. I need to stop when k equals n. So I'm going to do my dot, dot, dot there. And I'm not going to write down the very last term. I'm going to let's write down the penultimate term. So let's write down what the expression is when k is equal to n minus 1. So just before the nth term, right? So the n minus 1th term is the one that I'm going to write down here. So if k is equal to n minus 1, then I would have n minus 1 plus 1. So my denominator would be n. And then again, if this is n, if k is n minus 1, then n minus 1 plus 2 is n plus 1. And my numerators are still the same. So this expression here is what I obtained by replacing k with n minus 1, right? And then I need the sum of the first n terms, so I'm then going to do plus, and then in parentheses, if I replace k with n, I end up with 1 over, let me look back, this should be a minus, right? And then I'll have n plus 1, and then minus 1 over n plus 2. So that's the nth term in my nth partial sum. Right? Now remember, we're adding all these things together. Well, the interesting thing is that if I look at the second term in the first pair of parentheses, that's the negative of the first term in the second pair of parentheses. So right here I have a negative 1/3, but then I'm adding 1/3. So these actually cancel out. And then look at what's going to happen here. The negative 1/4 will cancel out with the 1/4. So those go away. And then even though I don't write it, I know that in the next pair of parentheses, I'll have a positive 1/5 that will cancel out with this negative 1/5, right? And then similarly here, in the pair of parentheses that's before this one, I know that right here there would be a negative 1 over n term, which will cancel out with this positive 1 over n term. And then here the pattern continues right until that last pair, right? Because I have negative 1 over n plus 1 plus 1 over n plus 1. So again, those completely go away. This process here, where it's like all the intermediate terms, they just they collapse on each other like a folding telescope, and that's why we refer to this as a telescoping or a telescopic series. So all but two terms cancel out. The 1/2 is still there, right? There's no negative 1/2 anywhere else in this. And then this negative or minus 1 over n plus 2 also remains. So even though it looked like this really complicated expression, our s sub n is simply 1/2 minus 1 over n plus 2, right? And this is our formula for s sub n, all right? So once we have our formula for s sub n, now the next thing is to ask ourselves what happens to this nth partial sum as n gets very, very large. So if I want to now figure out what essentially the entire series sums up to, if it does sum up to a number, then I would have to take the limit of s sub n as n goes to infinity, right? So in fact, let me write it like this, and I'll write everything in one line so you can see how it progresses. So this was our original series. So the 1 over k plus 1 minus 1 over k plus 2. And then what did we find out? We found out that the sum of the first n terms was in fact, let me write this down. All right, so we did this. Now, these aren't entirely equal. There's a reason why I left the space there. There's something that I have to write there to make them equal. But we figured that this was that 1/2 minus 1 over n plus 2, right? So if I want to now figure out what the full series is, what I have to do is take the limit of this as n goes to infinity, which in turn is the limit of this as n goes to infinity, right? So again, you figure out your partial sum, right? And in this case, we have this nice property of these telescoping series that most of the terms will cancel out. In fact, all we're left with are just these two terms. So these are those two finite number of terms that the definition is saying. It's saying no matter what my n is, right, we will always have this property that the sum of the first n terms will always simplify to something that looks like this. And then after finding your s sub n, you take a limit to see what happens as n goes to infinity. So in this case, as n goes to infinity, this term approaches 0, and we're left with 1/2 minus 0, so that's 1/2. So that means this series converges to 1/2, right? So therefore, our series 1 over k plus 1 minus 1 over k plus 2 converges to 1/2, right? This method, this idea of again where you have all the cancellation that of all the kind of intermediate terms, if you will, that process is referred to as the method of differences, right? So this process, in fact, let me write it right beside what we did. I don't want you to think that this down here is the method of differences. The method of differences is right here, right? Because you have all these differences that cancel out. So this is often referred to as the method of differences, right? And it applies very well to telescoping series. Now, the thing with telescoping series is that you can't always assume that it's the consecutive terms that are going to cancel out like this, right? Sometimes it's not the consecutive terms. And so take a look at this example. Right, so let's take a look at this series. So let's say k goes, again, let's start at 1 to infinity. And suppose I have now the square root of k plus 2 minus the square root of k plus 4. All right. So suppose I have this as my series, right? Let's see if the method of difference works, right? And then if that method of differences work, then we should be able to find a formula for S sub n. So S sub n, or nth partial sum, is this summation, right? K going from 1 to n, and we have the terms of our series. So again, let's list these vertically and see what's going to happen. Well, when k is equal to 1, we're going to have the the square root of 3 minus the square root of 5. In fact, let me write it over here. So this term is what we get by plugging in k equals 1. And then to that, I have to add another term when k is equal to 2. When k is equal to 2, and I won't simplify it too much. I'm just going to write it as root 4 and then minus root 6. Well, look at that. It doesn't really cancel out. Right? So it's like, uh-oh, is this really going to work? Well, you know, we're a little bit stubborn. We're persistent. We're going to keep on going and see what happens. Because sometimes you do have to do a little bit more in order to see patterns. When k is equal to 3, then we would have the square root of 5 and then minus the square root of 7. Right? So this is what I get when I plug k equals 3 in. And then suddenly I see something. Look, I have my negative root 5 there, and then a positive root 5 there. Maybe this is what we need after all. So I'm going to write a few more terms, right, so that we can really see this pattern. If we plug k equals 4 in, we're going to have the square root of 6 minus the square root of 8. And then, so this one, when k is equal to 4. Now, if you notice, see, the other thing too is when you do it vertically, you know, I mean, actually, you could do it horizontally. It doesn't matter, but you can definitely see the pattern in the first number in the parentheses, and then the second number in the parentheses. It's root 3, root 4, root 5, root 6, and then over here you have root 5, root 6, root 7, root 8, right? And then look, we have a minus root 6 and then a plus root 6. So I think things will cancel out. The difference now is there is a gap between what will cancel out. So I'm going to write out a few more terms here because I want you to be very, very clear as to what will cancel. And then what I'm going to do, when I do my dot, 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 I'm going to start with the very last term when k is equal to 1, when k is equal to n, and I'm going to work backwards. And then I'll write down what value of k I plugged in. So over here, if I plug k equals n in, I'll have the square root of k plus, the square root of n plus 2. So we'll have the square root of n plus 2, and then minus the square root of n plus 4. Then if I plug k equals n minus 1 in, then I basically have to subtract 1 from this. So I would end up having the square root of n plus 1 minus the square root of n plus 3. And then keep going out again. Let's go back one more term. And then the square root of n minus the square root of n plus 2, right? So I've written out a few more terms just to help us see the pattern. So this is the term that we get by replacing k with 5. This one now, the very last one, is what we get by replacing k with n. This one, I replaced k with n minus 1. This one, I replaced k with n minus 2. But now we can see how things will cancel out. So I'm just going to circle things, that way I don't draw too many messy things. So this one, root 5, negative root 5, there is the positive root 5. Negative root 6, there is a positive root 6. Negative root 7, there is a positive root 7. So what would come after the term that would be in the next pair of parentheses here will cancel out with this. And then the term that comes after that would cancel out with this. Right? And this is where we have to generalize the pattern, because we don't have n is not a fixed number, right? So we have to be able to write down this symbolic expression for s sub n. That's one of the big things in the telescoping series, the ability to write down that explicit, that simplified formula for s sub n, right? And then now, if you do this working backwards, so notice what happens. This cancels out with this. This will cancel out with the term that would be in the pair of parentheses prior to this one. And then this will be canceled out with that one. So what we're left with is a root 3, a root 4, a minus root n plus 3, and then a minus root n plus 4. So all of this, it just collapses, it simplifies to this expression. Root 3 plus root 4 minus root n plus 3 minus root n plus 4. Right? And that's the formula for s sub n for our original series. Right? It does telescope, but here we have to write out a few more terms to see that telescopic pattern. Right? Now once we have this, we have to find the limit of s sub n to see if our original series converges. Right? So let's take our limit as n goes to infinity of our nth partial sum, which we have right here. Root 3 plus root 4 minus root n plus 3 minus root n plus 4. Well, these two are constant terms, but as n gets very, very large, both of these get very, very large. So this goes off to positive infinity. This goes off to positive infinity. So we end up with basically this type of expression. Root 3 plus root 4 minus infinity minus another infinity. And then we end up, so this one converges or diverges, right? Because it goes to negative infinity, right? So this series diverges. Right? So that's the two-step process for dealing with our telescoping series. Very similar to the two-step process for our improper integrals, where we first did. So remember, in improper integrals, where we had a positive infinity at the upper limit, we replaced that positive infinity with a placeholder b, and then we computed our definite integral, and then we took a limit of that, what we called our area function. Well, it's the same process here. We start with an infinite series, and what do? We replace that infinity with this number n, this nth partial sum. And we try to simplify that as much as we can using algebra, right? This method of differences, and then take a limit of that to see whether or not our series converges or diverges. All right? Let's do one more example of this. And let's see. So in this example, it shows another little twist that can come up in these uh, telescoping series. Right? So let's take a look at this one. So let's say the sum is k going from 1 to infinity of 1 over, let's say, k squared plus 3k plus 2. Right? Now, the thing with this is that I don't see anything that's like I don't see any negatives here that's going to force terms to cancel out, right? That's a little it's not working out, because if I write these out as it is, when k is equal to 1, I'm going to have 1 over, and then I'll have 1 plus 3, that's 4, plus 2, that's 6. So I'll have 1/6. When k is equal to 2, I will have 1 over 4 plus 6, that's 10, plus 2, that's 12. So I'll have this. So I'm not seeing how anything is going to cancel out. Let's write down one more term. So when k is equal to 3, I'll have 9 plus another 9, so that's 18 plus 2, that's 20. And then so on. So I don't see anything where this method of difference will work. And the trick here is that we need a way to break this single fraction up into two smaller fractions. That sounds like some partial fraction decomposition to me. And that's the trick to get this method of difference to work, right? So if you're given something like this where it's just a single fraction, right? We're going to try to do partial fraction decomposition and see if somehow a minus comes up in this, right? So using our partial fraction decomposition, so let's factor that denominator. And that one looks like it factors as k plus 1, k plus 2. And so then both of these are simple linear factors. So we know the decomposition has to be of this form: a over k plus 1 plus b over k plus 2. Let's clear our fractions. So we'll have a 1 on this side. Multiplying the first fraction by this denominator leaves a times k plus 2. Multiplying the second fraction by the same denominator leaves b times k plus 1. And then we can use our method of choosing convenient values of k so as to simplify or eliminate one of the terms on the right, so we can solve for the other constant. So I'll start by letting k equals -1. So if we let k equals -1, this side is a constant, so it remains 1. And then this just ends up being a, because it's a times 1. And then here we'll have plus b times 0. So the constant in that case is 1. And then let's let k equals -2. That will eliminate this term, and it will allow me to solve for b. Okay? Again, that's the power of having an identity. You know that it's true for any value of your variable. So on this side, we'll still have 1. And then that's equivalent to, so now this we have a times 0 plus, and then b times -1. So this means that -b is identical to 1, which means b is identical to -1. And there's the negative that we need for our method of differences, right? So in fact, what we've shown is that the terms of this series, right, can be decomposed into these two simpler fractions. A over k plus 1 minus b, minus 1 over k plus 2. Right? So yeah, so then I think we see where this will work. So Let me write down the original series. So 1 going from k to infinity. We have the 1 over k squared plus 3k plus 2. So that's now, using our partial fraction decomposition, is the same as this series. 1 over k plus 1 minus 1 over k plus 2. Right? So now let's find out our nth partial sum. So our nth partial sum is the sum as k goes from 1 to n of this expression. And that should be easier to compute now that we have the minus sign there. That's what's going to give us that telescoping property. So let's write out the first few terms and see just how many terms we need to write down to see the pattern of cancellation. So when k is equal to 1, we have 1/2 minus 1/3. When k is equal to 2, we have 1/3 minus 1/4. Well, there we go. We don't have to go too far to see the cancellation. I'll do one more pair at the start, and then I'll do the last two pairs in our nth partial sum. When k is equal to 3, we'll have 1/4 minus 1/5. Then let's do our dot, dot, dot. And if you want, it sometimes helps to start with the very last term and then work backwards. Again, just to make sure that we have the right pattern here. And then we'll have 1 over, so if I replace k with n, I have n plus 1 minus 1 over n plus 2. Then working backwards, notice if we work backwards, the denominators get smaller. They go down by 1 each time. So if that's the case, then this denominator will be 1 over n, and this denominator will be 1 over n plus 1. And that's pretty much all that I need, right? So in terms of our method of differences, that negative 1/3 and the positive 1/3, that negative 1/4 and the positive 1/4. Negative 1/5, and then there's going to be a positive 1/5 after that one. Working backwards, we have the 1 over n plus 1 and the minus 1 over n plus 1. And then in this pair of parentheses prior to this one, we'll have a negative 1 over n that will cancel out with that positive 1 over n. So our method of difference tells us now that this nth partial sum simplifies to 1/2 minus 1 over n plus 2. Right? And then, if we take a limit of this, I think we see what's going to happen. Right? So, the limit as n goes to infinity of s sub n is the limit as n goes to infinity of 1/2 minus 1 over n plus 2. This term here, right, approaches 0. So we end up getting 1/2 minus 0. So that is equal to 1/2. So our original series, right, so therefore our series k going from 1 to n of 1 over, and remember it was that k squared plus 3k plus 2, this series, I wrote the partial sum. The full series now is what is equal to, or converges to, right? So that series converges to 1/2. Right? So that's the telescoping series. It requires a little bit of algebra, right, to get it to work. And unlike the geometric series, we don't always we don't have a nice specific form that it fits, but instead it has this property where this method of differences always simplifies to like the same number of terms, right? But you just have to be careful. We saw that example where it wasn't like the consecutive terms that canceled out. There was like a gap. So you might have to write a few more terms down in order to see that pattern. because most questions regarding telescoping series will be like a two-parter. The first part is going to ask you to do the algebra, which is right here, right? To find a formula for S sub n. And then the second part now is going to say, using that formula for S sub n, determine if the series converges. So that's where you do the calculus. So you got the algebra there, the calculus there. Again, make sure that you're clear on what you're doing at each step. All right, so our journey through infinite series will continue, and I hope you continue along with me. I'll see you in the next video.